So welcome back to the HVAC-Engineering-Techie channel. This is the channel where we talk all things HVAC, from engineering design, construction, equipment systems, test and balance extensively, controls, efficiency, and system performance. These videos are intended to be educational in nature to help you with your career. Also helps you in the field to know better what you're doing. Today's lesson is on tab, performing duct traverse Pitot readings. Basically, we go over everything you need to know about how to lay out and how to actually take a Pitot reading. And I think it'll be very interesting to you. But before we do, I'd like to ask a favor. Please become a subscriber if you haven't already to this channel. Give me a thumbs up if you would. And the reason is Google uses that data to evaluate this video and my videos on the channel. And it really helps me. I appreciate it. It's free to you. It costs you nothing. And I promise I won't bug you. Thanks. I appreciate it. So let's get started on how you do Pitot readings. Thanks. Okay, so let's start talking about how you do Pitots. And what we're doing basically is trying to find the velocity of the air in the duct. We're trying to find the average velocity. That's what a Pitot is all about. And we're trying to do that accurately. So to do that, we take a lot of readings inside a duct to tell what the average velocity in the duct is. So remember that the airflow in the middle should be faster than the airflow near the edge, where the resistance of the metal is causing it to slow down. So remember, again, we'll go over it one more time. Total pressure equals static pressure plus velocity pressure. And these are the three ones. This is total pressure. This is the one that has the pressure of the air flowing down the duct. It also includes the pressure of the air trying to escape the duct, which is static pressure. So it has velocity pressure and static pressure. This one is just static pressure because it's just reading the air trying to get out of the duct, which is static. This one is velocity pressure, and it's actually reading total pressure, but because we have the backside connected to the static pressure, it subtracts that. So this becomes just velocity pressure. And that's what we're looking for, is a velocity pressure of the air, because that's how we can tell what the velocity is. Remember, the Pitot tube is a double wall tube, and the inner tube is connected to an open hole on the end, and it catches that velocity pressure, that velocity coming down the duct, and puts it down here to the bottom tube, which is the total pressure port. And then there's some holes around the outer tube here that take the static pressure reading, and it puts it in this port here. So we can now hook up like this. We can hook this one to the static part of it, and we can hook this one to this part, and we can now read velocity pressure directly. And this is what a flow meter would look like, or a data meter. So you hook it up to a Pitot, and this is how you hook it up, and that'll give you your readings. Now, most of these meters are calibrated to give it to you in feet per minute, so they'll do the conversion for you. But if you have a meter that's not capable, or like you're using a Magna-Healy gauge, which is possibly fine, there's nothing wrong with that, then you have to do the convert to velocity. And remember, that formula is velocity equals 4,005 times the square root of velocity pressure at standard conditions, which remember is 70 degrees at sea level. So if you're doing a Pitot at 6,000 feet, this ain't the formula. You got to use the 1,000, I guess 97 if I remember, times the square root of velocity pressure divided by the density of the air. But anyway, most of your instruments will do this all automatically. You need to make sure that's what your instrument does. So then, here it is. The velocity equals 1,096 times the square root of velocity pressure over density, where the velocity pressure is in inches of water gauge, density is in pounds per cubic feet, and the velocity is in feet per minute. And that's what we need, the feet per minute. All right, so finding flow. So flow times the CFM is equal to the duct area in square feet times the air velocity in feet per minute. Now, your meter can't do this for you because it won't know what the duct area is. So this is why we do Pitots and how we do a Pitot. So we will take a bunch of readings inside a duct to get an average air velocity, and then we'll multiply that times the duct area in square feet. So average velocity times the duct interior area. Now, that interior area is important in case this duct has liner, or in case it's a double wall duct. So you need the inside dimension, is the dimension you're dealing with both for your Pitot and both for your calculation. Now you can do a single point measurement where you just measure one point. It's not very accurate because it won't give you a total average. It's just giving you a single point, but that's certainly possible to do. And in very small ducts, that's basically what we do because you only need 1 point. So this is mini measurement. So this happens to be a log layout, and we'll describe what those two layouts are in a minute. But you can see we have these holes we drilled in the duct, and we've drilled them in certain spaces according to our layout, and I'll explain what the layout is in a little bit. So we drill these holes, and then we'll put our pitot in, and we'll measure at each one of these spots. So then we have 6 readings here, and we have 6 readings here. Is this 6 or 5? I think this is 5. Yeah, it's 5. So we have 5 on this side and 6 on this side. And so basically we'll read at each one of these points. And when we're done, we'll have a reading for every one of those points, and then we'll average them all. And you can set your meter up to data log this, so it'll do that automatically. I normally don't do that. I normally read and write down every answer, even though I may have it stored in the meter, because I want to see what these points are as I go through. So this is basically how we do a layout. So here's an example. Say we have a 24 by 36 inch duct with an average velocity of 983. We've already done our pitot, and the average of all those readings is 983 feet per minute, would be the CFM. So it's 24 by 36 inches, which equals 864 inches. But we need to turn that to square feet, so we divide by 144, 12 by 12, right? So that equals 6 square feet. So 983 feet per minute times 6 square feet equals 5,898 CFM. And that's how we get the CFM after we've done a pitot. So here's a typical layout, which we do before we get to the site. And this layout, this happens to be a equal area one. So this is not a log layout, but it is a equal layout. So basically we found the duct size, and we've laid it out for each, so we know exactly how many readings we have to have. And so then on this particular one, we see we have 1, 2, 3, 4, 5. We have the 5 laid out here. And then what we do is we mark the pitot. This happens to be an airfoil. And we normally take and mark it. Either you can do it with a felt tip pin, or you can do it with a little piece of black tape. And you basically mark off the dimensions that you're going to read across this thing. You have this all hooked up to your meter back here, which I don't show. And then you begin to take your pitot and you read the first reading, the first black tape. And take that reading and put it into the sheet. And then you take the next one and you read that one, and you put it into the sheet. And you go ahead and continue to do that across this, take your readings. And basically you just put it in, push the button to take a reading. And once it reads, if you're using a gauge, you let it settle, a few seconds to let it settle, make sure it's not bouncing around. And then you do the next one, and then you do the last one. Now there's a couple things you notice that we're holding this airfoil level, because we don't want it going all crooked anyway. We want to read these points as close as we can, so you keep it level. And what we're trying to do is get an average. So then we take and go to the next one, next one, next one, next one. We read all these until we get all these filled out. Now the reason I try to look at them as I go is I want to make sure I don't have any weird readings, because sometimes you'll get an area of turbulence. There'll be some turbulence here, and you could actually get a 0 reading or even a negative reading, which means the air goes backwards. So those you want to watch out for, which means when you start having that trouble, it means you're not taking it in a correct, your location of your pitot is incorrect. And it may mean there is no good space to take a pitot. It's possible, because you don't have enough space. Anyway, this is the basic way you do all pitots, no matter whether they're round, square, flat, oval. The basic process is just like I said here. So how do you get high accuracy? Well, number one, laminar flow, and that's what I was alluding to. So 4 to 6 diameters straight upstream and 2 to 4 stream downstream. So if you have a nice square elbow with nice turning vanes in it, and you've got fairly good flow, so it means it's fairly even flow, you don't have much trouble. We still want to get down here so we don't have this high velocity jet. We want it to kind of be evened out. So that's why we want to be 6 diameters. And diameter means the small dimension of the duct. So if you have a 24 by 12, you'd want to be at least 6 feet down from this elbow and 4 upstream of any other thing. Whatever you have, if you had anything else down here, you'd want to be 4 diameters up. And this is be a practicality where you want to take your pitot. And all you're trying to do is get in nice laminar flow. Now, if you have a duct like this, which is a round duct without veins, and the air is going to push up to the top, so you're going to have some really weird flows. You still get 6 and 4 diameters. You're trying to get down to where you're more laminar. So obviously on a duct like this, the further down you go, the better off you are, because you don't want to be here because you'll have these real high velocity jets here. And you don't want to be where you have a coil or something. You don't want to try to do it. Well, right downstream of a coil may not be too bad because that coil may act as a straightener for the air. But you would never want to be right next to a damper because that'll be high velocity jets and it will not be laminar flow. So that's important to lay out very constant flow during the test. So you want to verify you have a constant flow. You don't want to have the VFD on and modulating that fan because that's not what you want to do. You're trying to find a maximum value of that duct. So you need to lock, if it has a VFD, you need to lock it in position. And if you have any other control device like damper upstream, you need to lock it in position so it's not messing with your pitot. Hold the pitot level, that's for each reading, and square, so you're going to get those points as good as you can. And another item is to don't dilly-dally. You don't want to go so fast you're not getting good readings, but you don't want to do this slowly. You're trying to get an average reading of an instantaneous point in time. And so that's, obviously you can't do total instantaneous, but you just go at a steady pace and get the pitot done. Look at readings as you take them and record them. Watch for turbulent flow, which can cause 0 or negative readings. And that's what I was telling you why I look as I go, so not to have that. If you want to increase accuracy, you can read the number of readings, increase the number of readings. So like if you laid out a duct and you had 30 readings, take 60 readings, you get a lot more accuracy. Or take more than one pitot. Take it and then take it again and then take it again and average the 3 readings. And you will get more and more accurate as you go. Normally, a good pitot is going to be plus or minus 3%, plus minus 5%. It's not going to be a 1% reading. It's just not going to be. It's just the nature of the beast is not going to be. But if you do it correctly and you do it as accurately as you can, you will have an accurate reading as long as you're not in turbulent flow. Okay, there are 2 types of duct pitots. There's a standard equal area. Actually, there was a research did a study on these traverses, set up a lab experiment with perfectly laminar flow, knew exactly what the flow was, has total instantaneous on it, and he did both of these types. And this type, the equal area type, which is the traditional type, the one that's been around the longest, it overestimates flow 3 to 4.5%. That was his statistical analysis. 4.6%, sorry. So it overestimates, the readings from it are high. And this is the equal area method, when it divides up the duct into equal squares, or the round duct into equal area segments. So each of these segments actually has the same area, it's just they're round quadrants. And that's the equal area. Then there's the Choibachef. I'm not sure if I'm pronouncing that correctly, but make it easy, it's the log method. And the log method underestimates flow 0.6 to 2.3%. So the log method is actually more accurate. So a lot of test and balance guys don't use it because it's a lot harder, not a lot harder, but it's more rigorous and you take more readings. That's why it's a little more accurate. It's a little more accurate because it has more readings in closer to the edge of the duct. So this is not an equal area. It's trying to take and get this frictionless, all the trouble is around the outside of the duct, and it's trying to take more readings in that area and less in this area. And so it's slightly more accurate. Now, between 4% and 2%, to me, that's great. I don't need to be super accurate. But now, if they're in turbulent areas, these accuracies are out the window. These are accuracies on total laminar flow. So the differences between these 2 types, you see this takes squares. This does not have equal squares. It has it puts more in the perimeter than it does the interior. This has equal area. This one has not equal area also. You'll notice that those areas are bigger than others, this in area. But you notice this takes 1, 2, this takes 3 readings for a round duct, where this only takes 2. 1, you put it in here, and you put it in here, you only have 2. So when you're doing a round duct, you drill 1 hole, and you have your probe marked for each one of these holes as you go across. So you'll do one real close to the edge, and one a little further in, and then to this last one right here. And then it's the same way. Then you have to do one this way, and then you have to do one this way. So, and in the equal areas, you just do one this way and do one this way. So round ducts a little bit more problem if they're big ducts and they're horizontal ducts. You got to have space to get to them. You may have to, if you have a great big duct and you don't have space, you may have to do one up to middle and then one down to the middle to actually get enough of them. But that's basically the layouts for the 2 types of Pitots. And we're going to show you how to lay out both of these. So standard equal area test. Here's the equal areas. Say this has 4 by 6. And we have charts on how to do this. And you're just taking the reading at the center of every one of these squares. So this is really easy to lay out because it's just equal areas. And some guys actually have airfoils with measurements on them. It has a scale on it. But most of us just mark it so we can tell what it is. And these are the equal area method. And then this chart here, which I don't want to get too cumbersome here, let me catch up to us, is a chart on how to lay out equal area. And so what it's saying here is it's telling you that equal area is pretty easy to lay out, right? You measure the duct. You know, this is one dimension of the duct, and this is another dimension of the duct. So this chart goes to 96 inches and 144 inches. So it doesn't matter which way this duct is going. And it tells you if you got a 6-inch duct and it's 1 square, which is 6 by 6, you can do 1 Pitot reading, right? Now you can also do more in a 6 by 6. You could do 4 readings. You could do 2-inch readings. So down here it says that if you want to use smaller squares, permissible. Larger squares are not permissible, but smaller ones are. So basically this is what this chart is telling you is this is how many squares. So if you want to do a reading of a 96 by 144 duct, it's 384 readings. So it's a whole bunch of readings. So this is not, what's really important here is to know that you need 6-inch squares. Or if you got a duct that doesn't come out even 6-inch, just pick 4 inches. You can pick anything smaller than 6 inches, not bigger. So if you got bigger, you got to do 6-inch squares across it. So this is fairly easy layout for a square duct. And this is standard areas for round duct. And so if a duct is 5 to 9 inches, it will need 6 readings in both areas. So you're going to have 1, 2, 3, 4, 5, 6. And six in the horizontal and 6 in the vertical. Now if you have a bigger duct, you have 10 to 12 inches, you're going to read 8 readings in both dimensions. This is, anywhere in between that, you're going to do 8 readings. If you have a bigger duct, 14 to 72 inch, you're going to do 10 readings in each position. And this is actually a chart that makes it a little bit easier. This goes to a 72-inch duct, I think. Catching up here. Yeah, a 72-inch duct. And you'll see what this is telling you. This is the 10 readings. And what it's saying is that these are the dimensions from the edge nearest you. The edge where you're inserting your probe, these are the actual dimensions, percentage dimensions to it. See, so like if you have a 2 by 2 duct, you got 1 reading, of course, that's all you got. If you've got a duct diameter of 12 inches, so this first one is 12 inches, and you got it, you're going to do 8 readings. And these are the dimensions. So you start off at 0.4 inches, 1.28 inches, 2.38 inches, and you go clear over to 11.6 inches. That's how you lay out on your probe. so you're getting the right depth of your probe. And this goes on down to the bigger diameters and tells you what it is. So this is a way, this chart actually gives you the actual dimension. So these are charts I've made to lay out to make it easy for the field techs to do this in the field. Now the Toibachoff, the log one is a little bit more difficult. It's actually pretty easy, but you have to lay it out in the field. I mean, lay it out in the office. You're not going to do this in the field. You could, but it's a little bit harder. So here you have a square one, rectangular duct, and here's the formula for it. So basically these are percentages. If you have less than 30 inches, then the first reading is you multiply the dimension times 0.074, the next one times 0.288, the next one 0.5, the next one 712, the next one 926. So these are actually just dimension percentages, and you measure the dimension and then you get your dimension to put on your airfoil. So it tells you how to do it. If you have the 30 to 36, then these are the percentages to take. And if you have greater than 36, these are the other ones. So you have to lay it out. And the way we always do it is take a form. The form you're going to report it on and make the layout there. So the guys in the field don't have to do any layout. So the guys in the field just look at the form and say, okay, here's the dimension layout. I know how to do this, Pitot. So how to perform the test for the log Toibachoff round duct. So now this one has a little bit problem because it has so many axes, and they're a lot harder to access. And this is actually why a lot of techs don't use the log method. It's a little harder to do in the field, and for the couple of percent accuracy it gains you, I don't think it buys you a lot. I think the square duct is a little more accurate, but round duct, it may be more accurate, but it's just a little bit more trouble to do. And here's the same dimension, the same type of thing on the log that we had for the square duct. The round duct, this is basically less than 10 inches, and it has, the first one you multiply by 0.032, the second one times 0.135, the next one 0.321, the next one 0.679, the next one 0.865, and the last one times 0.968. And that gets you your 6 readings for the first one. Now, if you have a 10 inch to 18 inch, then these are the numbers you use. And then this is the 18 inch, and it gives you those are the numbers to use. Now, if you have a hard time seeing these little numbers on whatever size screen you're watching this on, what you can always do is just stop your computer and clip this out of there, take a screenshot, or take a snip and snip this and then print it. So you can get all this data. You don't have to try to squint to see it. You can just get it right off the screen. So this is how you do the log type layout. Flat oval duct, separate the rectangular from the round. So basically remember that a flat oval duct is basically a square duct without walls, and a half a round duct on this side and a half a round duct on this side. So you basically split it into 2 types of readings. So this one, actually, by the way, it doesn't make any sense to do a log test on a flat oval because you don't have a wall here. So what we always did is just do equal area for the square duct and then do half the round here and half the round here. You've already done this face, so this gives you average readings here, this gives you average readings here, and this gives you average readings inside. And this is the best you can do for a flat oval duct. Let's talk a little bit about drilling and plugging the test holes. It's always best to do these, if you can, to do the test plug holes on the top and the side, not the bottom. But if you have to do, you have to do it. On an air conditioning duct, it's not a big deal, but on an exhaust duct, especially an industrial exhaust duct, it could be a problem. You might have some liquids in the bottom of the duct, and they may not be friendly liquids. Especially if you're working in a electronic manufacturing facility, you'll be really careful with this because on a lot of their exhaust ducts, it has acid in it, and this acid is very bad stuff. So you don't want to drill into that and get this stuff on you. And when you cut a hole in those ducts on the bottom, unless you cap them permanently, they could leak in the future. So basically, we try to keep our holes on top and on the side, but on a lot of air conditioning ducts, you can't get to the top, so you have to use the bottom no matter what. But no matter what, you have to plug the holes when you're done. You shouldn't leave open holes. And we use Normally we use plastic plug holes. Have these plastic plugs we buy. They're real cheap. I think I buy 1,000 for $10 or so. It depends. So you need to make sure your holes are, I have two sizes. I have 3/8 and 1/2 inch, depending on what size of airfoil you're using or size of pitot probe you're using. They also have a problem. You need to look at the type of duct. What material is this duct? Is this duct just galvanized sheet metal? Then the plastic ones are probably fine. Are they outside? The plastic ones may not be fine because the sun may eat them up. Or if you're in a stainless steel duct, plastic ones are probably not going to be fine. There's a reason the duct's stainless steel, and it will probably need some kind of stainless steel plugs. For those kind of ducts, hopefully the specification has specified hole plugs, which are basically steel or stainless steel plugs with a latch on them that open up. So you permanently affix them to the duct, and they open and close, and then you could take a pitot anytime in the future at those pitot holes. And those are only specified for stainless steel duct or PVC duct that has a problem, or fiberglass duct. So this has to be worked out ahead of time, so you know what your hole plug situation is, what you need to use. So the duct material might be galvanized steel, fiberglass or PVC, or stainless steel. Verify the air does not carry dangerous gases or liquids. And the liquids problem is only on an exhaust system, depending on what it is. So that's basically how you lay out a flat oval duct. So you want to verify your pitots, and the way you verify a pitot is trying to find another reading somewhere else or another pitot so they can do it. You can compare them to total grill flow. You can compare what happens between your pitot and the total grill flow. There would be duct leakage, so you should have a difference. Your pitot should be more than the downstream grills, slightly, not a lot, but slightly. If your pitot is less than the grills downstream, I suspect you have an accuracy problem. Instrument calibration could be a problem. The flow head calibration, if it's off, or if your pitot instrument is off, you could have a difference. You want to compare the fan curve. So if you're taking a pitot on a unit and you're downstream, you want to check and see what the fan says is flowing. And that's a comparison to your pitot. Curve accuracy is not as accurate as other things, but if they're close, you feel good about that. Compare to coil flow. So you have a pressure drop on a new coil. You can compare the flow to that. It needs to be a clean coil. Compare to return airflows plus outside airflows. If you have some good way of measuring these already, or if you've done other pitots on those and you add those together, well, okay, that's good. The pitot accuracy itself is what we're trying to determine. Was this an accurate pitot or not? You don't want to blindly trust your pitot. You want to verify. It's trust and verify, but you don't want to trust the pitot because it could have an accuracy problem. It could throw off the thought process in your balance, in reviewing your balance. So you want to make sure you have an accurate pitot. So if you take a pitot and that's all you have to verify this unit flow, then the reading is questionable. If you have the pitot plus you got another reading that verifies your pitot, you feel a lot better. I got two things that come together, I feel a lot better. If you have the pitot plus two other things, you're absolutely sure that your pitot is accurate. So that's what I'm saying. You got only one reading, is questionable. Two is feel much better. Three, no question. And that's how you do it. So there's another way to do that, and that's comparison to multiple pitots. So you could take the pitot 3 or 4 times, and if they all come up similar, then you can have good confidence that it's a good pitot. Now, if it has some flow problems, they're not going to come out the same. If you have turbulent flow, that turbulent flow varies all the time, so you won't get them to compare. But if you do, you can. Another way, of course, is to take more readings in the pitot or take more pitots. So here, let's take a look at the forms. Now, these happen to be my old forms, so the way these look doesn't mean anything. It's just what they are. This is a sample rectangular duct. You can see it has readings over here, and what we would do is put the dimensions in here, place the dimensions so we know what the dimensions are, so he knows how many readings to take. This is a round duct one. You can place the dimensions over here. And so this is the readings we're going to capture. And this happens to be a flat oval one, which has the round down here and the square up here. So these are just my forms, and down here they listed the final number, the final flow number of the Pitot. And these go in the report just to back up the Pitot. So they're pretty simple forms, and they're easy to do. And you may have an automated system that do the forms automatically. But in either case, it's good to lay it out this way. So that's HVAC Pitots. And I hope that was informative and you learned something there. So thanks for watching. Have a great day. Don't forget to become a subscriber to the channel. I would really appreciate it. Have a great day, and I'll catch you on the next one.